Hi guys, today I'm going to talk about the TurboScan software. So before we get started, I just want to give an overview on how the TurboScan system works. So on this slide here, I've got the micro gas turbine, with the two sensors attached. One sensor to the compressor and one to the turbine. That's connected to the TurboScan acquisition unit and then to a PC, a Windows PC, which has the TurboScan software. So the way it works is the accelerometer measures the vibration, which gets transmitted to the acquisition unit, and that data gets processed and sent to the software, and then you'll see all the data essentially being processed and displayed on a number of charts on the software. So once you download the zip file from our website, you can extract the zip file into a directory on your PC. In my case, it's on the C drive, and you'll see a number of files being extracted. You can click on the application and actually right click and send that to your start bar or desktop ready to go. So I have the icon set up on my desktop, so I'll double click on that to start the software. So the splash screen and the warning, click I agree, and the software will start. And so you'll see a typical screen that we have in our suite of software. Looks very similar to the software in our Platinum suite. So essentially you'll have a number of tabs, and these tabs display the data which is being measured from the accelerometer. So in the first tab, Spectrum, it essentially shows the vibration level, which is the vertical axis here, which is shown in millimeters per second squared. It's a funny unit, but it's essentially a measure of the vibration energy measured from the turbine. On the horizontal axis is the frequency. So what does this actually mean? Well, there's a good website on the internet which describes how vibration gets transformed into something called the frequency domain. So in this image, you'll see that the vibration measured from the turbine, in other words, the overall machine vibration, looks like a very sort of jaggedy signal. What the software does, it actually breaks the signal down into its various independent components, which look like these sine waves. These sine waves each have their own frequency, and so the software takes these individual components and plots it onto a chart which has the frequency component on the horizontal axis and the magnitude of that frequency component. And that's what you see in our software. So you'll have the magnitude of a vibration and the corresponding frequency component. That's all well and good, but to make things a lot easier for you to interpret, what we've included is values onto the right-hand side. They call the RMS values, which is essentially just an average sum of the vibration levels in the signal. So it's an average of all these frequency components into one number. So you'll see there's two types of RMS values. There's one which is millimeters per second squared, which is actually an acceleration value, and another value which is millimeters per second, which is a velocity. So they are correlated. We tend to use the acceleration for high frequency range and velocity for low frequency range. But overall, we just use them as an average measure on how bad the vibration is in the system. So in this window, you'll see that it's broken into two components, the compressor and turbine, corresponding to obviously the compressor and turbine accelerometers. So when you run the engine, you'll see the vibration levels displayed on these charts for each compressor and turbine. So what I'll do is I'll select the TurboScan device. In this case, I'm just going to select my PC speaker to simulate the TurboScan. So I'll select the device, click Start. Right, and as you can see, as I'm talking, it's actually breaking my speech which is a form of vibration, into its various frequency components. So a bit about the tools on the screen here. So you'll notice that when you hover over the chart, you'll see a number of buttons which appear. These are just tool buttons essentially that you can use to alter the display. You can pause the display, you can play, you can move things around, you can save the image. There are tools for adjusting the colors of the display, etc., etc. You can zoom in by actually selecting the window here and selecting it again and press play, and you can see here that it has a much closer view of the display. You can enlarge the axes, you can actually bring it back to its default level, etc., etc. So it's fairly user intuitive. On the right hand side we have buttons which control the software for selecting the device, which is the very first thing you do, starting the recording, pausing the recording, starting it again. You can take a snapshot of the window and save it as a bitmap or other. That's very handy for future reference. You could also say pause the display, and you can actually save the data. So if I click on save, you can save the data as a CSV file. And so what that does, it exports the actual values in the screen into CSV format. And we'll show you later how to extract the information from that. The clear data is more to do with the response curves later on to actually reset the recordings, etc. So that's a bit of an overview of the control window. The window settings down here, settings and open don't work currently. They will in future versions. Exit is quite obvious. What we have at the top is a timestamp for when you're actually running your turbine test. Your turbine name, so obviously you want to record the type of turbine you're testing. You might want to enter the ECU turbine runtime. So for example, when you're doing the test, your turbine might be at 15 hours runtime. And you want to enter the speed of the turbine when you're taking recordings. So let's say, for example, I want to record the vibration roughly at idle. So let's say it's 45,000 RPM. So you enter that. That RPM gets translated into a running speed in hertz. Okay. You could also enter the turbine EGT, the exhaust gas temperature. So that might be in the order of 600 degrees, whatever it might be on the day. So that's just an overview on how that works. And the reason why it's important to enter this data is that when you save the data as a snapshot, or if you save it here, you want to be able to actually record the conditions of the test. So that every time you do test, you're testing at the same conditions, and that's quite important. So moving right along onto the next tab, which is the waterfall. So the waterfall essentially is taking those initial graphs shown on the spectrum and plots it into a different form. As you can see, it's more like a radar echo graph where it shows you the magnitudes of the vibration over time. So that could be useful for looking at patterns within the vibration, etc. On the next tab, we have the raw signal. As you can see, that as I'm speaking, it's taking vibration essentially from my voice and displaying that raw signal in real time. And the good thing about this system is it's a very, very fast real-time system. It works extremely well. It's great for measuring vibration levels from machinery, etc. So yeah, it's a good indication on what's going on in the system. As I'll talk, I'm going to pause right there, and I'm going to show you another feature. On all our graphs, if you hover over the chart, you'll see that the values will show. So that's probably a good way of checking, vibration levels at the horizontal axis location. So it's a very good way of looking at that data very quickly. If I click start again, it will continue. So moving along again into the hardware. So this is the information used to set up the TurboScan device. As you can see, that the sample rate of the recordings. Again, you really don't need to change these values. You can just leave them at default. The resolution of recordings, the type of FFT window, we recommend just leaving it as default. You can average the signal when you're taking measurements, so that if you're finding that the signal is changing too rapidly, you can actually increase the averaging, which slows down the change in the signal. But anyway, overall, leave these as default. It works just as well. The turbine tab, this is an interesting one. So when we actually take recordings of the vibration levels in the turbine, we kind of want to have an idea of what those peaks are in the chart. So in the spectrum chart, as you're taking recordings, you'll see these peaks that appear. These peaks actually do correspond to an artifact or a feature in the turbine. It's a very common sort of thing that you see in vibration analysis. So the way we actually understand what those components are, we can actually define the physical quantity or definition of the turbine. Such things as, for your compressor, how many blades does your compressor have? Okay. Your turbine, how many blades does your turbine have? The ball bearings within inside the engine, if you have access to that data, and that data is quite difficult to obtain from manufacturers, but if you do have access, you can define the ball bearings such as, the number of balls in the bearing, the diameters of the bearing, the pitch diameter, which is defined in this little image, D, and the contact angle. So obviously the angle the ball makes with the mating surfaces of the ball races. So once you have that information, again, it is quite difficult to obtain. So yeah, you have to bear with me on that one, unfortunately. What actually happens, this information gets translated into something called the critical frequencies. So these critical frequencies define the particular artifacts or defects that might occur inside the engine. So for example, if you're running the engine at speed and you're constantly seeing a critical frequency of the ball bearing occurring at 3,000 hertz or 3 kilohertz, that will appear as a very high peak in the chart, say here. If you see a very high peak at 3 kilohertz, it's most likely corresponding to a particular defect, such as a ball defect or an inner race defect, whatever it might be. Okay, so this is just a guide to help you understand what is going on. Now, obviously, it's a bit more complex than that, but this is just a simple guide just to help you understand what is happening. There are other frequencies that occur, such as, an out of balance condition. So with an out of balance, you'll see huge peaks pretty much at the same RPM as a turbine. You may have other things like mechanical looseness, which will occur at these frequencies. You also have compressor blade pass, which is essentially the air rushing past each blade of the compressor, and the same for the turbine. So these are just a guide to help you understand, what the frequencies you're seeing in the chart. Now for the final tab, it's called the response tab. Click start, and now I can actually show you how to use the clear button. So clear will start clearing the graphs or the chart and start recording. So what you'll see is that as you run the turbine, you'll actually be measuring the RMS values or acceleration over time. And this is a very handy thing to have. What you can actually do is start the turbine at idle and slowly ramp up the turbine to full throttle and then ramp it down again. And what it will do, it will actually give you the vibration response of the turbine. So a lot of turbines have what we call harmonics. So I'm just going to stop this for now and show you what that is. So move this across. So each turbine has some kind of harmonics, and what do I mean by harmonics? Well, it's the same thing as, say, a tuning fork. When you hit a tuning fork, it will vibrate. Now, the thing is, the turbine can be considered as a system of, say, two tuning forks, simplistically. So one end is the compressor tuning fork, and I guess one in the turbine. So if the compressor is vibrating, its vibration signal is actually transmitted through the shaft and into the turbine, and vice versa. So you'll find that when the turbine starts to resonate at a certain speed or a certain frequency, it will start to increase its vibration level. So when it increases its vibration level, you'll see that as a peak in the graph here. So we have an example to show you of some measurements we took from a real turbine. So what we did was we ran this turbine from idle up to full throttle and then back down again. So we want to do that quite slowly, just so that we can record a nice curve without seeing any sort of sharp peaks. So we started at idle and slowly ramped up the throttle from past half throttle all the way up to full throttle and then down again. As you go down, you start seeing the peak. It goes back down in idle. So it's quite interesting to see that on this particular turbine, in this case this was a Wren 54 Mark III, from idle, as it increased in speed, we could start seeing that the vibration level starts to increase for both the compressor and the turbine sides. And as we went beyond, say, half throttle, then the vibration levels started to come down a bit. So it just goes to show that certain turbines have different critical frequencies or resonance during their throttle curves. And it's just something interesting to note, I guess, when you're operating a turbine. You might see a bit of vibration or sort of rough running at a certain speed, and then once you go past it, it runs quite smoothly. So it's a good way of actually just even looking at the performance of your turbine to see how it's performing during the throttle setting. So I'll click start again. So once you have this information, again, you can save the data as a CSV file for future reference, or you can take a snapshot. Again, you can save that. So that's a really sort of handy feature to have. Okay, so once we've recorded the data and we saved it into the CSV file, we can actually post-process the CSV file. So here's a sample file that I downloaded when I was running the Wren turbine at full speed or full throttle. So I'll double click on that. I don't need to convert it. So you'll see the file. It'll have series information. You've got the date and time that you ran the turbine name, the RPM that you measured the data, exhaust gas temperature, and the RMS values for the compressor and turbine values too. So all that stuff is there for future reference. So now to convert the spectrum data to something that is useful, you can select the data for the compressor. So you can highlight those two rows and then go to the top and go insert, charts and line, and the Excel will basically chart out the spectrum data. And that's really good. You can actually go through and have a look at the data in detail. So that's for the compressor. You can do the same thing for the turbine. So the turbine is located below the compressor data. It's the same thing. You can select this data here and do the same. Get insert, charts there, and that's the turbine data. So it's very handy. Keep this for future reference. This will basically monitor the health of your turbine over time. and hopefully show any sort of particular issues as you go. So you can save this file somewhere as an Excel file, or keep it as CSV. So it's up to you and how you want to store it. So I won't save that. Okay. To exit the software, yeah, it's just clicking on the exit button essentially, and that should shut down.